I can graph a sequence and name its domain and range. Here's what you need to know. The domain of a sequence is made up of the terms positions. The range of a sequence is made up of the terms values. So in this sequence of even numbers 2, 4, 6, 8, 10, and then goes on forever, the domain would be the first term, second term, third term, fourth term, fifth term. Our domain is all of the natural numbers, 1, 2, 3, 4, 5, because those are the numbers of terms that we have in the sequence. The range is the actual value of those terms. So the 2, 4, 6, 8, and 10 that you see, those make up the range of the sequence. So our range in words would be all even integers greater than or equal to 2. In order to graph a sequence, you're going to take the domain and the range together. So we'll plot the term's number or its position in the list as your x-coordinate. And you'll plot the actual value of that term on the y-axis as your y-coordinate. So for example, our first term is 2, so that's going to be 1 on the x-axis to represent term number 1. And it's going to be 2 on the y-axis because the value of that term is 2. So if we were to plot all of these points, we would have the point 1, 2, 2, 4, 3, 6, 4, 8, and 5, 10. And the way that we would read this is we would say, for example, this one, the fourth term is 8. The third term is 6, and so on. Here's an example. State the domain and range of this sequence and then graph it. So we do need to make sure that when we're reading our sequence, we know if it's finite or infinite. This one does not have the little dot, dot, dot at the end. That means this sequence is finite. It does not keep going on forever. The only thing that we have in this sequence is the 6 terms that you see. So when we plot this thing, you're only going to have 6 points on the graph. We'll start by stating the domain, which would be the values 1 through 6, because there are 6 terms. And then the range is the actual values themselves. And if I were to plot those points, I'm going to have the point 1, 3.1, 2, 3.6, and so on. We match the domain value to its corresponding range value. And so the points would look a little something like this. And notice that they do make a straight line right here. That's going to be important a little bit later on in this unit. Pause and try this one. State the domain and range of the sequence, then graph it. Your domain would be 1 through 5. Your range would be the actual term values. And then we will match those points up to plot them on the graph. So you have the point 1, 1, 2, 3, 3, 9, 4, 27, and 5, 81. And notice that this graph, if we were to connect the dots, we would have a curved graph right here. We aren't connecting them though because we are listing very specific points. This is not the equation of a line or anything like that, so we do not connect our graph. Your next learning target, I can classify a sequence as arithmetic, geometric, or neither. Here's the difference. An arithmetic sequence is a type of sequence whose pattern is a common difference. That means that you add or subtract the same thing every time. Linear functions also have common differences. So arithmetic sequences can be represented by linear functions. Arithmetic matches with linear. The graph of an arithmetic sequence will be linear. It will be a straight line when you plot the points. On the other side over here, a geometric sequence is a type of sequence whose pattern is a common ratio. Exponential functions also have common ratios. So geometric sequences can be represented by exponential functions. And the graph of a geometric sequence will be exponential. It will have that curved shape. Here's an example. Classify our sequence as arithmetic, geometric, or neither. This is the one from the previous learning target. This time we have the sequence going on and on forever, so I could continue to plot points if I wanted to. This would keep going. And we're going to notice the shape of this right here. If we were to connect these dots, I want to know if it would make a linear shape or an exponential shape, and that's going to help us match up either arithmetic or geometric. One way that we can take a look at that is to look at the actual terms or the points themselves. Each term is 0.5 or 5/10 more than the one that comes before it. So we can say we have a common difference of 0.5. That's what we're adding every single time. So our graph is a straight line. That means our sequence is arithmetic. It makes a linear shape on the graph, a straight line, because we're adding the same amount between terms every single time. Your slope is constant. Pause and try this one. If you wanted to pull up the graph, here's what it would look like. And we noticed before that this does take a curvy shape, but we can also look at the pattern of the sequence. Each term is 3 times the one that comes before it. So we follow the pattern of times 3 every single time we switch terms. That means we have a common ratio of 3. The graph is a curved line. This sequence is geometric because it makes an exponential shape when we graph it, and that shape is because we have a common ratio of 3 between our terms. If you want more on this topic, be sure to check out the Learning Target spreadsheet for additional resources, videos, and practice.